Welcome to AP Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be looking at the first couple of sections of Chapter 5 and our beginning of our notes for this chapter. Now, Chapter 5 deals with thermochemistry, and this is kind of like last chapter where we got into solutions in that there are some aspects of thermochemistry we're going to look at first semester because we'll need it to understand certain things we're going to see in upcoming chapters. But there's also other aspects of thermochemistry that we need some more chemistry to totally understand. So this is a split chapter. We're going to be looking at some aspects of thermochemistry in Chapter 5 and some of them in Chapter 19, which is the second to last chapter at the end of the year. Now, when you take a look at what part of the AP test deals with thermochemistry, it's one of the heavier represented concepts. This is one of the big five in AP chemistry is thermochemistry. So on the old version of the AP test, typically about 7 out of the 75 questions on the multiple choice portion of the test was related to thermochemistry. And in the FRQ, there were questions every single year somewhere in the FRQ. And that probably will not change because it's one of the major aspects of chemistry. All changes in matter involve changes in energy. So first, the nature of energy. Thermodynamics, which is what we'll be talking about and studying in this chapter, is the study of energy and its transformations. And thermochemistry is the study of the relationships between chemical reactions and the energy changes involving heat. Now, energy is the ability to do work or to transfer heat. So really it comes in one of two forms. Energy used to move an object that has a certain mass is known as work, and energy used to cause the temperature of a substance or an object to rise or change is known as heat. So we have fundamentally two different types of energy that we're going to be studying, work and heat. And when we look at changes in the energy of a system, we have to look at the work component and that changes, if at all, and then the heat component that changes. Now, our fundamental types of energy are kinetic energy and potential energy. Kinetic energy would be the energy an object possesses based upon its motions. So translational, which means moving to a new location, vibrational, rotational, light, heat, electrical, are all different versions of kinetic energy. And we often relate the movements of the particles to the kinetic energy of those particles. So it's a concept we're going to be using often. Now, the actual kinetic energy equation is the kinetic energy of a moving object is 1/2 of its mass times its velocity squared. Now, if we're looking at SI units, the mass would be in kilograms and velocity would be meters per second, and we're going to square it. So if we're looking at units of energy, that must mean in SI units, we would have kilograms times meters squared over second squared. And we're going to abbreviate that to a unit you should have seen in first year chemistry known as a joule. And all of our various forms of energy will come back to this fundamental kilogram meter squared over second squared, which is the same thing as a joule. Now, potential energy is the energy an object possesses by virtue of its position or its chemical composition. When you're sitting up high, you have stored energy based upon your height because that object had to have at some point been moved to that high position, and therefore it stored that energy. So positional potential energy is one of the most fundamental types of potential energy. The energy of position would be the mass of the object times g, which is the force of gravity, times the height. And if we actually look at these things again and talk about SI units, mass would be kilograms. Gravity is a force, and force is going to be meters per second squared times height, which would be meters in SI units. Once again, we get back to the kilogram meter squared per second squared, which we typically measure as joules. So we're still talking about the same fundamental type of unit as when we were talking about kinetic energy. Another type of very important potential energy is electrostatic potential energy. And this is actually related to Coulomb's law, which we've talked about and will continue to talk about all year long. Now, in Coulomb's law, we're talking about the force. So it's a very similar but a subtly different equation, which we'll look at in a second. Now, energy spent as work moving an object against a force over a certain distance would be electrostatic potential energy. When we have two charged objects, so Q1 and Q2, and if it's oppositely charged, those things are going to be attracting each other. So as we're pulling these apart over this distance between the two of them, how much energy would it take to move these two charged particles apart? Now, in this particular case, d would represent the distance then between the ions, and k is what's called the proportionality constant. Now, fundamentally, with electrostatic potential energy, you just need to understand that when we're talking about overcoming attractions between like particles, um, this is energy we have to spend to move those particles farther apart. And the greater the distance, obviously, the more energy we have to spend. And also, the greater the charge difference between the two, the stronger they're going to attract each other, the more energy we have to spend. And this is something you need to understand conceptually. This isn't something we're going to be doing physical calculations of this type of energy. You just need to understand the qualitative aspects of what happens with charged particles and the energy involved in moving them farther apart. Now, this is actually closely related to the concept of Coulomb's law, but Coulomb's law was looking at the force of attraction between those two objects. So really the difference between this would be the fact that the force over a certain distance, so if we multiply this times a distance, well, instead of using our symbol meters, let's talk about distance as d here. Notice if we multiply Coulomb's law by d, what we get is exactly that. Force, which is Coulomb's law, attraction, times the distance over which we move it, we go from the Coulomb's law version of the equation to the energy form of the equation here. So there's a subtle difference between the two when we're talking about the force of attraction between objects, which is what we usually talk about with charged particles, and the energy with which we would have to spend to move particles farther apart or push them close together if they were like charged. Another important form of potential energy is chemical potential energy. And when we're looking at the energy involved in chemical reactions as we change from the reactants to the products, this is a very important energy in that type of situation. So it's energy stored in the arrangements of the atoms inside the compounds that make up our substances. So this is this energy stored within the bonds of the substance, those attractions between the atoms inside the compound, as well as attractions between each other here. Now, one thing about energy is while you can't create or destroy it, which you should remember from first year chemistry, which we'll coming back to in a second, that pops up in these notes, we can convert from one form of energy to another. So energy can be converted from positional potential energy, the bike stationary at the top of the hill, and then as it moves down the hill and the bike starts to move faster and faster and faster, that positional potential energy is being converted into energy of motion, kinetic energy. So in this case, the cyclist has potential energy at the top of the hill that's becoming kinetic energy as that cyclist moves down the hill. Now, when this happens, we're converting from one type of energy to another, but we're not actually creating or destroying any energy. And that's actually something that deals with what's called the first law of thermodynamics. So at the bottom of the hill, the potential energy based upon the height where she was on the top has now been converted into potential energy of the moving bicycle as it moves down. Now, I already took a quick look at this idea, but there's other types of energy besides joules that we're going to have to looking at. But the SI unit of energy is the joule, which is why we're so often in that type of unit. And remember, 1 joule is 1 kilogram times meters squared per second squared. And that's something that we already looked at. This is a really important idea for you to conceptualize. Because if you're doing an energy calculation, so let's say you're calculating the kinetic energy, and it requires you to be in joules, that means you have to be in SI units of kilograms, meters, and seconds in order for that to work. So be very, very, very cognizant of the fact that joule is an SI unit, and if you're ever in joules, we're talking kilograms, meters, and seconds. Now, an older non-SI unit that's still widely used is actually called the calorie. Now, notice this is calorie with a little c. 1 calorie is actually equal to 4.184 joules. So our SI unit is the joule. Our older non-SI unit that you'll see from time to time is the calorie. Now, don't confuse this with the calorie that you've heard of. And that's actually the food calorie. You'll notice it has a capital C here. So this is different from our little c calorie. A food calorie is actually a kilocalorie. When we're looking at units of energy in food, it's such a large number. If you actually reported it in true calories, they would be gigantic. So divide it by 1,000 and you end up with how many food calories you have. So a kilocalorie or a food calorie is equal to 1,000 little c calories. And those are the common types of units you're going to see. Or sometimes we'll see kilojoules when we're dealing with large amounts of joules. Now, important to understanding thermodynamics is understanding system and surroundings. The system includes the molecules that we want to study. So if we're looking at a chemical reaction for a molecule system, what we're really looking at as the system that we're studying is the actual atoms and molecules that are involved in the reaction. And typically the surroundings would literally be everything else in the universe. Here your important surroundings are the immediate surroundings, and that would be the cylinder and the piston. So really, the system in this case that we're studying is just the molecules that we're viewing. And part of the immediate surroundings would be what houses those molecules. In this case, the cylinder and the piston. But technically, the surroundings would be that and everything else inside the universe. And when we're looking at thermochemistry, we're looking at how energy moves between systems and surroundings. So we're looking at transferring energy. Now, I'd mentioned earlier that there are two different types of energy, work and heat. Energy used to move an object over some distance is what's known as work. So it would literally be the force you're fighting against. So if I'm lifting an object off the ground, the force I'm fighting against is gravity. And obviously, the greater the distance I move that object up in the air, the more work I'm going to end up doing. So work is force times distance. And force is often, as a unit, you'll see this from time to time, is a newton, which is a capital M. So when we're talking about newtons, we're talking about a force. And this is our SI unit. So that's going to lock us into very specific types of units in terms of kilograms, meters, and seconds. So force, which is the mass of an object times the acceleration. And acceleration would be meters per second squared. And since we're multiplying that times a mass, our unit of Newton is actually kilogram meter per second squared, which is what it would stand for. And if we multiply that times d, which is distance, which would be in meters, notice we get kilogram meter squared per second squared. We're back to talking about energy again. So remember, work is a kind of energy. Now, energy can also be transferred in the form of heat. And one thing about heat is heat deals with the motions of the particles inside our object. And heat will spontaneously flow from hot to cold. So heat always flows from warmer objects to cooler objects, like the idea that water flows downhill. Heat flows always from hot to cold. It's a spontaneous transfer of energy when cold touches hot. So if you touch the wall and it feels cold, you're spontaneously losing heat energy to the wall. Now, first law of thermodynamics is what section 5.2 kicks off with, which says that energy is neither created or destroyed. Law of conservation of energy is another name for this, and this is something we probably briefly talked about in first year chemistry. So in other words, what does this really stand for? Well, the total energy of the universe is constant. If we are constantly transferring energy from systems to surroundings and we can't create or destroy any of it, the universe would be systems plus surroundings. So if we can't create or destroy when we transfer, the total amount of energy then has to be constant. And if a system loses energy, that same amount of energy must be gained by the surroundings and vice versa. Now, the internal energy of a system is actually the sum of all the kinetic and potential energies of all the components of the system, and we call that E. Now, we don't directly measure E because it's a fairly complex thing, but we can look at changes in E, which we'll be coming back to. So internal energy would be the overall energy of the system. If we add up all the kinetic and potential energies, we get E. Now, by definition, the change in internal energy, which is written as delta E, so whenever you see this delta sign in front of some variable, that means we're looking at change in. So the change in energy of a system would be the final energy of the system minus the initial energy. And that would tell us how much it changed. And therefore, it would also establish sign. It makes a difference whether delta E is positive or negative because that's telling you whether the system is gaining or losing energy. Now, if delta E is greater than 0, that means that final energy was greater than initial internal energy, and therefore the system absorbed energy from the surroundings. So this is a gain of energy from the system's point of view. On the flip side, if the internal energy is less than 0, that must mean that final was less than initial, and therefore the system released energy to the surroundings. And over here, you're looking at over these last two things, what's known as an energy diagram. And we're going to use energy diagrams periodically throughout the course of the year. So you need to fundamentally understand the basics of an energy diagram. Now this is dealing with on the left side internal energy. So as we're going up, it's higher internal energy. Lower down will be lower internal energy. And notice the direction of the arrow. It's starting here and going that way. So that's telling us these are our initial substances, our reactants, and we're going to our final substance here, our products. And in this particular case, we are lowering the internal energy. So therefore, what must be happening is energy must be released as heat to the surroundings, and the overall internal energy of our products here is going to be lower than it was individually as a reactants. Now, from the first law of thermodynamics, when energy is exchanged between the system and the surroundings, its exchange is one of two things, either heat or energy. So really, when we're looking at delta E has to be Q plus W. What happened with heat, what happened with work is going to give us overall our change in internal energy. So if energy can be heat or work, and we have a change in internal energy, that meant we had to have changes in Q and changes in W. Now, this table is a nice summation of understanding the sign convention. In other words, what does it mean when you have a certain sign for Q's and W's and delta E's? Now, when Q is positive, that means the system is gaining energy. That's why it's positive, because the system gained. If the system is losing heat and sending it to the surroundings, then that means you have a negative value for Q. So positive when the system is gaining energy, and negative when the system is losing heat energy. Now, that one I think is conceptually easy for students to understand because you dealt with it last year, but work you probably didn't talk about last year in first year chemistry. So these next ones are much more important that you really internalize and think your way through because you do need to know this for this chapter. Now, when W is positive, that means work was done on the system. And that means the energy is absorbed, or the system is absorbing energy when work is done on it. So when W is positive, work is done on the system. When W is negative, that means work was done by the system on the surroundings, and the system is then spending that energy and losing it. That's why it's a negative from our energy point of view. So negative W means work was done by the system on the surroundings. Positive means the surroundings did work on the system. And overall, when we look at our total Q plus our total W for a certain situation, positive would mean a net gain of energy by the system, and negative would mean a net loss. And you have to look at both work and heat to understand your total change in energy. Now, when heat is absorbed by the system from the surroundings, we're specifically talking about heat here, not internal energy. So just heat, it's known as an endothermic process. So endothermic is something you should remember last year, and we were specifically talking about heat energy. If we're talking about whether the system gains or loses energy, that's endo and exergonic, which is not something we really get into in AP chemistry. It's kind of beyond the scope of what we normally talk about. But if you are gaining heat energy within the system, then that's endothermic, heat energy in. When heat is released by the system into the surroundings, then in other words, the system is losing energy, that would be exothermic. Now, the last thing we're going to get into here is state function. And just try and understand this at the simplest level. This is not a major important concept, but if you really understand it for what it is, it's a fairly basic thing. Now, usually we have no way of knowing the internal energy of a system, something I briefly mentioned before. And that's because it's really too hard to add up all those kinetic and potential energies. And it really depends upon the temperature and the pressure and the amount of matter. There are lots of variables here that make this a very difficult thing to actually calculate. However, we do know that the internal energy of the system is independent of the path by which the system achieved that situation or state or condition. So in the system below, water could have reached room temperature, 25 degrees Celsius. Remember that all year. When they talk about 25 degrees Celsius, that's our assumed temperature for room temperature. We could have had hot water that cooled off to 25 degrees Celsius. We could have had cold ice that warmed up to 25 degrees Celsius. So it didn't really matter how we arrived at that internal energy. At 25 degrees Celsius, 50 grams of water, the energy is what the energy is. So therefore, internal energy is what we call a state function. It depends only on the present state of the system. which would be like its temperature, its pressure, and so forth, not on the path by which the system arrived at that state. So a state function is anything that would be true. It only depends upon the current conditions and state. That's why we call it a state function, not upon how we got there. It didn't matter whether we had hot water that cooled off or cold water that warmed up. At 25 degrees Celsius, the delta E, or the energy, is what the energy is. So really what happens is the change in energy only depends upon what was our initial and what was our final value. It doesn't matter how those things changed over time. It's just what did we start at? What did we end up at? That would be delta E. Now, an analogy of what a state function is and how this would work. So here's a map of the Midwest. Let's say we were going from Chicago to Denver. Now, there's many routes by which we could move from Chicago to Denver. We could literally go all over the place to get from point A to point B. So it does make a difference in terms of the total distance traveled, what route we take. So distance is not a state function. Remember, state functions are things that are independent of path. They're only dependent upon what you started at and what you ended up at. So our actual distance is not a state function, but our change in altitude. So the altitude change, when we went from Chicago to Denver, it doesn't matter how many times we went up and down. Our actual change in altitude is going to be the same regardless of the route we took. It's going to be 4,684 feet difference between the two. So the change in altitude would be a state function, something that's independent of path. But the distance we traveled, the actual path we went, that's not a state function because it's not dependent upon, or I should say that change. It is dependent upon path. So how does this work with something like energy? Well, Q and W are not state functions because they're the path by which internal energy changes. So you can go through a variety of different situations dealing with changes in Q and change in W, but it's still not going to change the overall change in internal energy. So delta E is our state function, but the actual path by which internal energy changes, that is not a state function. That's our path, so to speak. So we could take a battery and we could just connect it with a wire and discharge all of the energy inside there in the form of heat. So we've got our initial energy here, we've got our final energy there. That change in energy was brought about simply by heat changes. So basically we lost heat energy. That wire heated up when you connect it from one to the other. We're not doing any useful work here. All we're really doing is losing energy that was stored inside that battery in the chemicals as heat. Or we could actually use it to do some work. So we could hook our battery up to, let's say, a fan. Now, we're moving the blades of the fan, so that involves work. And if you actually feel the battery while it's doing that work, it does actually heat up. So there's also some internal energy lost in the form of heat. Well, in those situations, whether it was all lost as heat or whether it's some heat or some work, when we go from the charged to discharged battery, the change in energy in both situations was the exact same. Even though we had different Q's and different W's, our paths were different. The overall delta E was the same between the two. So delta E would be an example of a state function. So whether it was shorted out and discharged or by running the fan, the delta E was the exact same. But in each case, the Q's and the W's would be different. Those were our paths. So other things that are state functions, pressure, volume, temperature, internal energy, which we just looked at, enthalpy, H, which will be coming back in this chapter. So it's heat changes at constant pressure. All those would be examples of state functions. And changes in them can be always expressed by final minus initial. And that ends our first notes over chapter 5.